Basically, those are the benefits associated with this chemistry. Let's talk a little bit now about how this battery would work. And so also on this slide, you can see the lithium-air cell showing both the charge and the discharge process. There's a magnification of the cathode. And what you see happening here is you see some gray. So this represents the cathode material, which is typically a porous carbon. You should also see a white blob, and this is meant to represent the reaction product. So this could be either lithium peroxide or a lithium oxygen phase, a lithium oxide phase. In most cases, it's the peroxide which is observed, and it forms as a result of reacting lithium, which is dissolved in the electrolyte, with oxygen, which is also dissolved in the electrolyte, and with an electron that comes through the cathode. So the mass advantage of this system, as you can see, is based on the fact that one of the reactants, oxygen, does not have to be stored on board. We can flow it in as we need it, and that's represented by the oxygen molecule on the far right edge of the slide. So we call this system, this type of battery, a precipitation dissolution system, because in the course of operating the battery, we nucleate and grow one of these peroxide or oxide phases. And then when we recharge the battery, this phase has to decompose or dissolve back into the electrolyte. So that's, of course, very different from the sort of mechanism, the intercalation mechanism we talked about in a lithium-ion battery, where, for example, in the cathode we had a rigid host where we would intercalate lithium ions into existing vacancies in that material. So here we're, making a new phase as we discharge the battery, and then that phase has to go away when we recharge. So that's a fundamentally different mechanism, and you can see that the creation and discharge, or creation and decomposition of this phase I would speculate it's going to be a slow process, and to some extent we see that in the rate capability or the power density of these batteries. So that's basically an allusion to one of the limitations of this system. Let's talk about some of the other limitations, some of the barriers to realizing these benefits in a real battery of the future. So I've already mentioned the power density issue. So you can see on the left, we've plotted the voltage as a function of charge state. And there's two lines here. The bottom curve represents the voltage we get out during discharge of the battery, around 2.7, 2.8 volts. And then when we go to recharge, you can see that we have to use a much greater potential, typically over 4 volts. So that hysteresis in the voltage capacity curve is basically telling us that we don't have a very efficient battery. For example, I'd have to put in maybe 100 units when I recharge the battery of energy, and I would get maybe 70 of those out during discharge. So about a 70% efficiency is typically one of the better lithium-air batteries at this point in time. And the main reason for this problem is the high potential during charging. We're not quite sure what's responsible at this point for that high potential. We call it an overpotential. There could be several mechanisms that lead to it, but that's one of the major areas of research right now, is trying to bring down that charging potential to sit almost right on top of the discharge potential. So that's one challenge, efficiency. A second challenge is shown to the right, and that's capacity retention. So in this case, we're plotting the capacity as a function of cycle number. And so you can see for early stages in the cycling process, maybe the first few cycles, we get a very high capacity, but then that falls off over time. And here again, there's some debate as to what's the mechanism responsible for this capacity loss. One possibility could be that when we form this peroxide or this oxide phase, that's an insulating film that prevents electron transport from occurring in the cathode. So basically the battery would shut down after that film gets beyond a certain critical thickness. Another possibility is that because we're dealing with a porous carbon cathode, a porous carbon support, those pores could fill up with the lithium peroxide and prevent or block any further reactions of lithium and oxygen. So like I said, there's some debate as to which mechanism, maybe some aspect of both are at play here, but solving the capacity, the efficiency problem, and there's a few others as well. We still have to deal with, for example, getting a pure source of oxygen on board the system. If we're flowing in air, we could have some nitrogen, we will have some nitrogen present. That could result in side reactions with lithium. Some water will be present. So do we really need a pure source of oxygen? And if so, how can we get that in a lightweight, efficient device? Also, to get maximum capacities, we'd like to have an anode, which is a monolith of lithium, so a pure metallic lithium anode. In that case, there are some challenges because we have to worry about dendrite formation. Like we talked about in the degradation discussion, we mentioned that lithium dendrites could form if we have a very thick SEI. And if we have a metallic lithium anode, the same process can occur, resulting in, say, short circuit to the battery. So as you can see, there's some pretty big opportunities associated with metal air batteries. However, there's some big challenges. And so what we're trying to do now, even in my group, is trying to understand the mechanisms that are responsible for these limitations so that we can convert this battery into something that's something that we play with at the lab scale on a lab bench right now into something that would be a viable battery for electric transportation.